So we're at the start of thermodynamics, okay? So what we want to talk about is a little something called energy and state functions, okay? And what energy and state functions are, essentially, are the beginnings and definitions of what we talk about with thermodynamics, okay? So, in energy and state functions, first thing we're going to talk about is energy, okay? And if you've taken physics at all, you know what the two types of energy that there are. There's kinetic energy and there's potential energy. Now with kinetic and potential energy, if you've studied physics, you know that the basics of kinetic energy are based on motion, okay? And the motion that we deal with kinetic energy, okay, is that energy is equal to 1/2 mass times velocity, okay? But this just means is how much energy an object has to be traveling in a certain energy, okay? For potential energy, okay, we're talking about positional energy. So that means how much energy is stored, potential energy. When we talk about potential energy, generally we talk about the example of a man walking up a mountain. How much potential energy does he have? Or if I hold this marker here and I drop it, the potential energy that was stored in here has a specific translation into kinetic energy once the potential starts turning into kinetic energy. Okay? That's what potential energy. Now, potential energy is defined as this. And that is, for potential energy, energy is equal to mass times acceleration times height. Okay? And when we talk about acceleration, we're normally talking about gravity that's associated with it. This is why potential energy on different planets with different gravity is going to be a little bit different. Okay? Now that you've all written that down, I'm going to say ignore that, because this isn't something that we use in chemistry. You're welcome. Sorry about that one. But for kinetic energy, all right, we're still talking about motion energy, all right? And for potential energy, all of this is generally energy that's stored in bonds. Okay? How much energy is stored in bonds is generally where we get the potential energy from, all right? When we break those bonds, generally, energy is being released or energy is being absorbed somehow. Okay? So that brings us to two states that we have to analyze in chemistry. Okay? And that is an exothermic state and an endothermic state. Now, for an exothermic state, when we have an exothermic state, the energy of the reactants is going to be less than the energy, it's going to be greater than the energy of the products. So what this means is that if I have a chemical reaction of A plus B, and this goes to C plus D, because my reactants had more energy than C plus D, and we know from thermodynamic laws that energy cannot be created or destroyed, energy has to be released at the end of the reaction. So, at the end here, we get energy. Okay? That E represents energy. Okay, so energy comes out of that reaction. If it's an endothermic process, the energy of the reactants is going to be less than the energy of the products. And what this means is that it's going to require some energy between a reaction of A and B to make C and D. Okay? So if you think about examples associated with this, if you burn gasoline, right, gasoline releases heat. If you've seen the explosions on all of these Hollywood videos, You see the explosion with the fire that's coming out, and that fire is exothermic energy. Okay? It's energy being released in the form of light that you're seeing it, and that's why you see those orange flames, right? But in any sort of gasoline explosion, or explosions in general, you're going to have a very exothermic process. Energy is going to be released somehow. In an endothermic process, and you might be wondering, well, where's the endothermic process? An endothermic process is something like any of those cold packs. If you were an athlete, or you've been at athletic games, and somebody's been hurt, and you take one of those packs and you smack the pack, and then you mix it up, you'll feel that getting cold. What that means is that you've got a solution, and as one thing's absorbed in the solution, it's endothermic, because it's sucking energy from the environment in order to solvate the material that's inside. So the pack becomes cold, and what that's doing is sucking energy from the environment. Now this is important to know, okay? Because once you have an example of energy, you have to sort of relate it to what's happening to the system and what's happening to the surroundings. Let me erase this and show you what I mean. So here's an example. All right, I have a system and I've got surroundings around it. Okay, the system is where the reaction is occurring. The surroundings are what is around it. Yeah. Okay. Sometimes you'll see this thing surroundings identified as the universe. Okay, you have the system and the universe surrounding it. Okay, we're going to call it surroundings right now, just to keep things a little simple for you guys. So if I have an endothermic reaction, the reaction that's occurring in the system is drawing energy in from its surroundings. So I'm going to color this in blue because we generally feel this as a cold entering the system. Okay, cold is going to enter the system for an exothermic process, or excuse me, endothermic process. Okay, that's why we feel those cold packs being cold. When I have an exothermic process, the system is actually expelling energy to the outside in the form of light or in the form of heat. Okay, so this is an exothermic process. You can't have both. You can't have a system that's endothermic and exothermic. Because generally we look at what happens at the beginning and what happens at the end. Sometimes you'll have endotherms and exotherms in the intermediates, in between the reaction. But for the most part, what we like doing is looking at the reaction as a whole and determining whether or not it's going to be exothermic or endothermic. Okay? One important definition that we're going to define now is that of water and its heat capacity. Okay? Water, if I have 1 gram of water, so here's 1 gram of H2O. Okay? And if water has a density of 1, then it's going to be 1 milliliter of HCl. H2O, not HCl, sorry. H2O. Science is basically really, on the planet Earth, it's really based on what we can do with water. Because it's abundant, it's easy to work with, and it's a nice reference material. Because we have so much of it. Unless you're in Southern California right now. But beyond that, everywhere else we've got plenty of water. Okay? The planet is covered 3/4 of 3/4 of the planet is covered in water. That's the oceans, right? So it's easy to get water. It's easy to purify water. So it's easy to analyze 1 gram of distilled water. It's something that scientists have been using for a very long time, and it makes a very nice benchmark. Because water is pretty much ubiquitous. There's a big word for you, ubiquitous, which means everywhere in the universe. It's on comets. We find it in nebula. It's floating around everywhere. Okay. But here's water. We have 1 gram of water. And we use a lot of references to water, okay? And one particular reference that we're going to use is something called the calorie. 1 calorie, and notice that this is a lowercase c, okay? 1 calorie is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. Okay? So the amount of energy it takes to raise 1 gram of water 1 degree Celsius. All right? This is also known as the specific heat of water. And specific heat is a more general application, because specific heat is how much it takes to raise 1 gram of any substance 1 degree C. Okay? So there we go. Right? Raise 1 gram of H2O, 1 degree C. All right? Now, some of you are wondering, well, that's a calorie. Well, why did you use lowercase c? That's because food people work in larger amounts. Okay? And when they started analyzing food for energy content, they started to realize that a lot of the calories that we're talking about, they were dealing with millions of calories. People don't like eating millions of calories. But they sort of came to a compromise and said, okay, I don't want to eat millions of calories, so let's use something that's a little bit larger as our base unit. And what their base unit is 1,000 calories, which is 1 kilocalorie, right? But again, kilocalorie is hard to say, so they don't like using kilocalorie. So instead they said, well, I've got kilocalorie here, and that's K, it's kilo, it's kind of important, so let's just call it something that will confuse nobody, right? So food calories are called calories with a capital C. Not confusing at all, right? Okay. So that's what a food calorie is, right? Now, for energy, however, something that we like to use is something called the joule. Right? And the joule has a certain amount of energy. And when I have 1 calorie, this is lowercase c, by the way, I'm going to have 4.184 joules. Okay? So 4.184 joules is also the amount, the specific heat of water. So depending upon what we work with, be it joules or be it calories, they're sort of interchangeable energy units. We use them a lot. I tend to fall into the joule category. So you hear me talking about joules quite often, but maybe not so much calories. Okay? But there you go. So if you're eating food, when you're looking at the calories, what you're actually consuming is kilocalories worth of energy. And if you think about it, you've got 1 calorie of water, or 1 gram of water. You've got a lot of more than 100 grams of water inside your body. Okay, so this amount of energy is really not that much energy. Okay, so I've taken too much time on this subject, so I'll break this up to a different video. In the second video of the series, I'm going to talk about state functions.